Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation with hyperbolic functions. In fact, we're starting it now. The previous video, which I highly recommend if you have not watched, you should watch it, is all about Euler's formula. And why that's necessary for this video becomes very apparent right from the get-go, because these two formulas right here were derived in the previous video. I highly recommend watching it. It's pretty neat. Anyhow, the question here now is, what if we decide to remove the imaginary numbers from the relations cosine of t is equal to e to the it plus e to the negative it over 2 and the sine of t formula? What if we were just to remove these i's here? You can keep the negatives, by the way, on the second term in those numerators. So instead of an e to the negative it, it'd be just e to the negative t. What would happen? Well, they definitely would not be the cosine of t and the sine of t anymore. And in fact, we would define a whole new series of functions based upon this slight yet significant change. And here we are at the hyperbolic functions. If we let t be a real number, then we define the hyperbolic functions to be the following. Notice they look, before I start naming them, notice they look very much like the original trig functions. We have what looks to be a sine, we have what looks to be a cosine, and so on and so forth down the line. So it looks like, I don't write my a's that way, so it's hard to do. It looks like we have all the regular old trig functions. But these are not trig functions because they're not based on the unit circle. But they're very close. So we define the sinh, which is the hyperbolic. That's what the h stands for. The h means it's the hyperbolic sign. We define the sinh to be e to the t minus e to the negative t over 2. That relation should be incredibly familiar. Remember, the sine of t was e to the it minus e to the negative it over 2i. So this is the sine function without the imaginary numbers, which seems like it should be more important, right? But it's actually not more important than the sine function. If there's importance that can be laid at the feet of any given function. The cosh, which is a hyperbolic cosine of t, is equal to, or defined to be, e to the t plus e to the negative t over 2. Now the rest of the hyperbolic functions I just define in terms of these two, just like you would in trigonometry. So the tanh, that's how you'd say that, is the sinh over the cosh. The cosech is the reciprocal of the sinh. The sech is the reciprocal of the cosh, and the coth is the reciprocal of the tanh. So these, once you know the names, it's not too terrible. And you do have to kind of memorize these two formulas there, very powerful formulas in mathematics. And if you, some instructors don't cover this material. Generally speaking, if an instructor does not cover this material, it's because they do not teach differential equations. I teach differential equations, and I can tell you sinh and cosh are very important. There are also applications, real-world applications that involve these functions. So it is incredibly important that we learn to deal with them sooner than later. Basically, anytime that you have a hanging chain or something like that, a lot of people think like a hanging chain in space is parabolic, or possibly, parabolic, but it's actually not parabolic, or they might think it's a hyperbola or something like that. It's actually not. These are hyperbolic functions. This would be the cosh, actually. And so that is anytime, and think about just hanging wires all over the place. There's hanging wires between telephone lines and stuff like that. Those are modeled using the cosh function, not a parabola or anything like that. So why do they call them hyperbolic functions? Well, let's show that if x is equal to cosh of t and y is equal to sinh of t, then x squared minus y squared is equal to 1. Now remember, with trig functions, which are called circular functions, x was equal to the cosine of t and y was equal to the sine of t. And t was an arc length along a unit circle, and the unit circle had the formula x squared plus y squared is equal to 1. And so that gave us the relation that cosine squared of t plus sine squared of t is equal to 1. That was the birthplace of that very important identity within trigonometry. Now we're saying there's a brand new formula in town, and this brand new formula is based not on the circular functions, which would be the cosine and the sine, but instead on these so-called hyperbolic functions. We want to prove that if x is equal to cosh of t, which is equal to, by definition, let me write it this way, cosh of t, which is equal to e to the t plus e to the negative t over 2. And if y is equal to sinh of t, which sinh of t is defined to be e to the t minus e to the negative t over 2, we're claiming that x squared minus y squared will be 1. That is, cosh squared minus sinh squared will equal 1. Well, let's find out. X squared is going to be e to the t plus e to the negative t squared over 2 squared, which is 4. And this looks very similar to the exercise we did at the end of last video. So this is going to be e to the 2t plus 2 plus e to the negative 2t, and that's all over 4. You can double check my mathematics there, but it is true. And y squared, which is e to the t minus e to the negative t squared over 2 squared, is going to be e to the 2t minus 2 plus e to the negative 2t over 4. And if you look at x squared minus y squared, well, we'll get that first picture, which is e to the 2t plus 2 plus e to the negative 2t over 4 minus e to the 2t minus 2 plus e to the negative 2t, again, over 4. And now you can do the subtraction. E to the 2t minus e to the 2t cancels. I'll do the back end first. E to the negative 2t minus e to the negative 2t. Those cancel. And then 2 minus a negative 2, that's a 4. And so again, this becomes a 4 over 4, which is 1. And this implies, again, that the cosh squared, same notation that we would use for a cosine squared, cosh squared of t minus sinh squared of t is equal to 1. That is the hyperbolic identity, and we call them the hyperbolic functions because the graph of x squared minus y squared equals 1 is actually a hyperbola. That is a hyperbola, and honestly, we only consider the right branch of that hyperbola. I'll graph the left branch as well, but for our purposes, the good branch that we're going to be dealing with here is the right branch. That's the branch that we deal with for hyperbolic functions. Okay. All right. So that's our first hyperbolic identity. And because we've proven it, there's no need for us to actually write out the proof here. We just proved it. But there it is. That's the hyperbolic identity. It's just like, or not just like, but it's similar to the Pythagorean identity for trig functions, where cosine squared plus sine squared is equal to 1. So you can see there are some similarities, not exactness, but some similarities between these two types of functions. Now, before we get to the next theorem, let's bring up something you might not have learned about the unit circle and trigonometric functions. And you may or may not have actually learned this, likely not though. Now, let's suppose that you're handed a unit circle. This is X, and here's 1, 0, and again, up above is Y-axis, and this point 0, 1. And you have some point, it's called the terminal point. It's terminal to this arc length t on the unit circle. And in the last video, I called that arc length theta. For now, just for this conversation, I'm going to call that arc length t. And we'll go ahead and draw in the line segment from the origin to that point P there. Try to get as exact as possible, but it actually doesn't matter how exact I am here. So I'll just get that point right there. And then, let's see, turn that off. We know that if on a unit circle, the arc is of length t, then the angle in radians is of measure t. So all that you should know from your trigonometry course. The one thing that maybe you never learned in your trig course that is very powerful here is the area of that sector. Now, the area formula becomes very important in Calc 2. The area of a sector, and a sector is just this pie-shaped region that I have. In fact, I'll highlight it. This pie-shaped region right here. That's the area of what we would call the area of a sector. Okay. So the area of that sector is equal to 1/2 the radius squared times the angle in radians. Now the radius of a unit circle is 1. So this is going to equal 1/2 times 1. And the angle on the unit circle equals the arc length that you're cutting out. It's basically the arc length subtended by that angle. And so the arc length being cut out is t. And so the area of that sector is t over 2. That is always the case on the unit circle, that if you have an arc length of, let's just pretend, 6, then the area that you have just highlighted is 3. It's half of the arc length. Nobody probably told you, probably were not told that, but it is true that the area is always half the arc length. Again, that only holds on the unit circle. Now we're going to relate that over to the hyperbolic functions. And I'm actually going to draw this before I start talking about this. Now what I've drawn is the right branch of the unit hyperbola, and that's x squared minus y squared is equal to 1. And what I'm going to do is plot a point on this right branch, and this point I will call P. P of x comma y. Now I do not want you to think that this is of length t, because that's not true. But what we are going to do is we're going to connect the origin via a line segment to that point xy. Now it's very important for this conversation for you to understand something. T is not going to be this angle. It is called the hyperbolic angle, but it is not that angle. T is also not going to be this arc length. So let's just start with that. T is neither the arc length nor is it the angle. That being said, let's go ahead and now look at this theorem. If we have a point xy on the right branch of the unit hyperbola, then x is equal to cosh of t and y is equal to the sinh of t. We're going to define that to be true. That is actually true as long as we use the definition given in this theorem. I shouldn't say that. The relation given in this theorem. We're going to let x equal cosh of t and y equals sinh of t. Now we've already, by the way, shown that cosh squared minus sinh squared is equal to 1. So we already do know that the x value is cosh and the y value is sinh. So it actually is true. But what is t? That's the real question. What the heck is t? T is twice the area of the region bounded by the x-axis, the hyperbola, and the line segment connecting the origin to the point xy. That is, T, if you took, T is twice the area. So if you look at this area right here that I'm highlighting, that's half of T. That is the relation. You're opening up an area of size T over 2. When you do that, the X value, that's the T that we're talking about for the cosh and the sinh. It's just the half, it's twice the area of this, or this is half the area of, half the value of T. And that relates back to what we talked about previously right here, that with the trig functions, you could technically define the trig function of a number T to be the point on the edge of the unit circle where the area cut out by the angle, or cut out by the sector, starting at 1, 0, all the way to that point, is half of T. And that's the same way we're defining it here. Kind of an interesting relation. Do most people understand that or memorize that? No, but it's a really neat relation that kind of links the two types of functions. So you have a lot of things that link cosine to cosh, sine to sinh, and those ideas to one another, the circular functions to the hyperbolic functions. But I think most students will just remember this. Oh, it's hyperbolic because it's x squared minus y squared is equal to 1. And it is true, but there's so much more to it than that. But I don't want you to think that that is going to be like a major part of your calculus course. Really, the most important pieces that we're going to be talking about that apply to calculus are the derivatives of the cosh and the sinh. But still, it is important, or would be nice, if you understood some of the theory behind the cosh and the sinh. Now, for the rest of this video, we're just going to play with these hyperbolic functions. So now we get into the mechanics of it, and I think at this point, students like this stuff much better than working with the theory behind the scenes of the hyperbolic functions. So let's go ahead and do this. Evaluate all hyperbolic functions at these two hyperbolic angles is what we call them, even though they're not angles in the traditional sense. So let's see. We're asked to evaluate the sinh of 0, the cosh of 0, and then the tanh, and the cosech, and the sech, and the coth, all of 0. But I just do these two because everything else is defined in terms of sinh and cosh. Well, sinh, remember, is e to the angle, or to the t, I should say, minus e to the negative t over 2. Well, that's e to the 0th is 1 minus e to the negative 0th is 1. So it's 1 minus 1 over 2, or 0. And cosh of 0 is e to the 0th plus e to the negative 0th over 2. That's 1 plus 1 over 2, or 2 over 2, which is 1. And now I can just say, okay, therefore the tanh of 0 is sinh of 0 over cosh of 0, and that's going to be 0 over 1, or 0. And now we have our reciprocal functions. So the cosech of 0 is undefined because it'd be something over 0. So we know that's undefined. And the sech of 0 is the reciprocal of the cosh, so that'll be 1. And the coth of 0 is the reciprocal of the tanh, and so that's undefined. So you still have undefined hyperbolic functions, just like you have undefined trigonometric functions. And let's go ahead and do one last one, that natural log of 5. So sinh of the natural log of 5, well, that's e raised to the natural log of 5 minus e to the negative natural log of 5 over 2. We know that at least in the first case, e to the natural log of 5, that's going to be 5 just by properties of logarithms and exponentials. So that's going to be 5 minus the second one here. Let me go ahead and highlight that in a different color. you have to kind of do a little bit of manipulation first. So that's e to the natural log of 5 to the negative first. All I did was take that exponent and put it into, I took that coefficient of negative and put it into the exponent. And now in the next move, I can simplify that to be 5 minus 5 to the negative first. It's supposed to be a 5. All over 2. It's just, you have to do that little pre-work. And then multiply top and bottom by 5, and you get 25 minus 1 over 10, or 24 tenths. And that reduces down, obviously, to 12 fifths. And therefore, by the way, I'll just write the cosec while I'm here. The cosec of the natural log of 5 must therefore be 5/12. Very nice. And now we'll do the cosh. Cosh of natural log of 5 is, again, big old fraction bar, e to the natural log of 5, which we know is going to be 5, plus e to the negative natural log of 5, all over 2. Just by beautiful symmetry here, I'm just going to go ahead and say this equals, I'm going to steal this notation right here, 5 plus 5 to the negative first over 2. Multiply top and bottom by 5, you get 25 plus 1 over 10, or 26 tenths, and that's 13 fifths. And therefore the sec of the natural log of 5 is equal to 5/13. Okay. And then finally, the tanh and the coth. Those are going to be pretty easy because they're just ratios of the sinh and the cosh. The tanh is going to be sinh over cosh, which is 12/13. And the coth, which I'll go ahead and write over here, the coth is the reciprocal of that. So this is how you would evaluate hyperbolic trig functions. Let's see, 13/12. There you go. So that's how you would evaluate hyperbolic trig functions. Kind of not too terrible. Generally speaking, they'd have to be either logarithms or nice numbers to evaluate them. You won't be able to evaluate by hand most hyperbolic functions, just like you can't evaluate trigonometric functions by hand. You don't know what the cosine of 2 is offhand. So that, just like you would need a calculator to evaluate that or approximate that, you would also need a calculator to approximate those using hyperbolic functions as well. You can also do calculus with these. Obviously, we're in a calculus class. We're going to do some calculus, right? So you can evaluate these using calculus. So take the limit as t goes to infinity of the coth. Well, that would be the limit as t wanders off to infinity of the, maybe I should write it this way, coth first. And I'll say that's the limit as t goes to infinity. Since I don't know a closed formula for it, I'll write it this way. It's the cosh of t over the sinh of t. And then that I could trade out for their formulas, exponential formulas. So the cosh is e, let me zoom in, otherwise my pen goes nutty, e to the t plus e to the negative t over 2, divided by the sinh, which is e to the t minus e to the negative t over 2. Multiply both numerator and denominator by 2. Notice I haven't done the calculus yet. These are just all cleanup steps. You get e to the t minus, or sorry, plus e to the negative t divided by e to the t minus e to the negative t. And then you would divide both numerator and denominator by e to the t. So if I do that, let me just showcase that move. Divide both numerator and denominator by e to the t. You get the following. That's the limit as t tends to infinity of 1 plus e to the negative 2t now over 1 minus e to the negative 2t. Technically speaking, you can bring those limits, into both the numerator and denominator. So if you're taking your time with this, let's say that you're in a class and your instructor really requires you to show every step with a limit, then this would be your next step. You break it into numerator and denominator. 1 minus e to the negative 2t. That's by limit laws. And then we know the limit of a sum is the sum of limits, as long as those limits are defined. So that's a limit as t goes to infinity of 1 plus the limit as t goes to infinity of e to the negative 2t all over limit as t goes to infinity of 1 minus the limit as t goes to infinity of e to the negative 2t. Usually by this point, I don't force my students to go through all these little steps, to be honest with you. And then we know that's 1. And we also have a theorem that tells us as t goes to infinity, e to the negative t goes to 0. So both of these are actually going to go to 0. So I'm just going to put this as 1 plus 0 over 1 minus 0. That's via direct substitution. Technically, it's not really direct substitution because you're not substituting in infinity. So, but it's equal to 1. So that's the limit as t goes to infinity of the coth, the hyperbolic cotangent. Now, what about the limit as t goes to 0 from the left-hand side? The second part of that question. Well, the limit, let me write that down. Limit as t goes to 0 from the left-hand side of the coth. Again, we could take our time and write out every little step here, but instead I'm going to steal a lot of my mathematics. So I got down to the following: e to the t plus e to the negative t. Let me write this down. E to the t plus e to the negative t over e to the t minus e to the negative t. So that's where we got before. Now, here's the deal. Can we just sub in 0? And the answer to that is no. If you were to substitute in 0, you would get 1 minus 1. And that's a problem. So we can't just willy-nilly sub in 0. And technically, you could do the same move we did before. It's not necessarily the best, but it works, I suppose. Let's say limit as t goes to 0 again from the left, and divide top and bottom by e to the t to get 1 plus e to the negative 2t over 1 minus e to the negative 2t. And now we have an issue. It's actually the same issue we had before. If you try to substitute in 0, you get that the denominator tends to 0. The numerator actually does not tend to 0. We can investigate this conceptually. As t goes to 0, e to the negative 2t, right here, will tend to e to the 0th or 1. Now, it is kind of important here to note your t is tending to 0 from the left-hand side. So you're like at negative 1/1,000,000th, that type of thing. And e to the negative 2 times negative 1/1,000,000th is e to the positive 2 over 1/1,000,000th. It is approaching 1, but from above. Now, it doesn't really matter for the numerator. And if you don't follow that, here's a easier way to see it. You have e to the negative 2t. It kind of looks like this, right? And you're allowing t to approach 0 from the left-hand side. So this is a height of 1. Notice our heights here are getting close to a height of 1, but they're still above 1. That's the whole point, is that these heights are still above 1. Same thing in the denominator, by the way. This e to the negative 2t in the denominator is approaching 1, but from above. That's critical to note because then we know this entire numerator is approaching 2, technically from above, but that doesn't actually matter. It's approaching a positive 2. And that entire denominator is approaching 0. 1 minus 1, but it's 1 minus a number slightly greater than 1, so it's approaching 0 from below. And so we know from our early work in calculus that a constant positive number over a number approaching 0 but still negative will be negative infinity. That's probably the easiest way to evaluate this. So the coth, the limit as t approaches 0 from the left of the coth, is going to be a negative infinity. Again, there are other ways to do this, but I like that conceptual way of doing it because it showcases your ability to think graphically, and I really rejoice with that. Now let's go ahead and use Desmos just to visualize the three base hyperbolic functions, the sinh, the cosh, and the tanh. Turns out that Desmos can graph those pretty easily. So here is the sinh of t. Now I want to draw your attention to a couple things here. If I graph y is equal to e to the t over 2, remember the sinh is actually e to the t minus e to the negative t, and that's all being divided by 2. So if I look at e to the positive t, but divide that by 2, notice the blue curve, and I'm actually going to go ahead and make it this way. I'm going to maybe do a dotted curve there. Notice that to the right, our sinh looks just like an e to the t over 2. And to the left, it should look like e to the, negative t, again, over 2. I'm sorry, and it's a minus because it's a cosh, or a sinh. So it's a minus e to the negative t. And let me make this colorful again. I'll make this blue and dot dashed. Notice to the left, it looks like that negative e to the negative t over 2. These are the guidelines to graphing, actually, for the sinh. Now remember the cosh, on the other hand. So the sinh, by the way, it kind of looks, a lot of students think, oh, the sinh looks like a cubic. And it kind of does, honestly. It's not, but it kind of does. If you trade that out for a cosh, notice the cosh. A lot of students, again, will say, oh, it looks like a parabola lifted up 1 unit. It's not a parabola. The right branch of it actually follows e to the t over 2. And remember, the cosh is e to the t plus e to the negative t. So I remove that minus on the e to the negative t. And you'll see the left branch of it follows e to the negative t over 2. So these are actually exponential on both sides. They're not parabolic, they're exponential. They grow faster than a parabola. You can kind of see, if I had to graph y equals x squared plus 2, or plus 1, I'm sorry. That's the purple function. But eventually, this right here is the cosh. Eventually the cosh rises faster than the parabola because the cosh is based upon exponentials. So anyhow, and then finally we have the tanh. Now the tanh is going to be sort of worthless to graph these two, so I'm just going to turn them off and we'll just take a look at the tanh itself. Here's the tanh right here. And a lot of students think this looks like the inverse tangent, which I guess it sort of does. The tanh eventually is reaching a height of 1. It doesn't actually reach that height of 1, but it gets too close to it. It's just that Desmos here rounds quite a bit. It approaches a height of 1. It's never actually at a height of 1. There we go. Okay. So there's the tanh. So the tanh sort of looks like a inverse tangent, and the cosh sort of looks like a parabola lifted up 1 unit, even though it's not, because it's exponential. And the sinh sort of looks like a cubic, but again, it's not. Remembering those graphs allows us to talk about the domain of the sinh and cosh and tanh very nicely. Remember, the sinh kind of looked like this. It's based on the exponential function, so sinh and cosh and tanh all can take any real number as their input. The tanh, you might be wondering, well, how does the tanh you might be wondering, I'm not sure if you are wondering this, but you might be wondering, like, how does the tanh allow for any input when the tangent doesn't, right? The tangent has domain issues. Well, one, the tanh is not the tangent. Two, let me finish drawing this out. I need to think as I draw. Two, the tangent, it's being divided by a cosine function. The tanh is being divided by a cosh. And the cosh function, if you're dividing by the cosh function, so sinh over cosh is e to the t plus e to the negative t over 2. And this will never be 0. An exponential plus an exponential will never be 0. So you're never really going to be dividing by 0. So that's why the tanh can take any real number as its input. Then you could see the range of the sinh is all real numbers. The range of the cosh, it starts at a value of 1 and climbs to infinity. That's why the range of the cosh is 1 to infinity. And the range of the tanh is -1 to 1, but not including those edge points. So very, very nice way to remember those domains and ranges. Now, as I mentioned earlier, this is the end of this video, but as I mentioned earlier, hyperbolic functions are useful for like hanging wires, stuff like that. That's models that can be used, that hyperbolic functions can be used for. They're also useful whenever energy is being absorbed or extinguished gradually. So that would be like light, velocity, electricity, radioactivity, that type of thing. Hyperbolic functions are useful in those situations. And then you'll see sometimes that velocity of ocean waves are measured using hyperbolic tangent functions, actually. So anyhow, this is kind of our gentle introduction to hyperbolic functions. We haven't done too much in the way of calculus other than the limits. In the next video, I think we're going to delve into, let me just double check, the hyperbolic identities, and then we'll go into derivatives.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.